In modern cyber warfare, a line of code is a physical force. It can spin a turbine, open a floodgate, or shut down cities. The bridge connecting the digital and physical worlds is known as Industrial Control Systems, or ICS. ICS is a broad category of computer networks designed to directly manage automated physical equipment. While standard computing infrastructure relies on network routers and servers to move data, industrial infrastructure uses hardware to maintain physical necessities, managing electricity generation, water treatment, and manufacturing processes. A specific, highly distributed subset of ICS is called Supervisory Control and Data Acquisition, or SCADA. SCADA systems regulate these mechanical processes across wide geographical areas and infrastructural networks. You interact with the results of SCADA systems every day. They manage operations within specific facilities, regulating the heating, air conditioning, and energy output in the buildings you work and live in. Because these physical services rely entirely on SCADA networks, a software flaw translates directly into a kinetic, real-world consequence. For decades, the primary defense mechanism for these industrial systems was security through obscurity. Facility operators assumed that utilizing proprietary, industry-specific interfaces and communication protocols kept outsiders at bay. Because the systems were so specialized, an attacker needed deep insider knowledge or an enormous amount of time simply to understand how a specific facility's SCADA hardware operated. The information age dismantled that barrier. Today, equipment manuals, internal architectural documents, and detailed hardware specifications are easily accessible online. Relying on obscurity reveals a critical flaw. Because these proprietary systems were historically unexposed to the public, they lack the rigorous real-world security testing that open-source or standard IT networks undergo. To understand the modern fragility of our physical infrastructure, we have to forensically deconstruct two major system failures. One, an intentional malicious attack, and the other, a cascading systemic glitch. For cybersecurity professionals, digital forensics can no longer stop at the server rack. It must accurately map the physical topology of the industrial systems themselves. This diagram maps the standard architecture of a SCADA network an operator or attacker must navigate. The brain of the operation sits in the control center, including the human-machine interface and engineering workstations. Below the workstations is the Master Terminal Unit, or MTU. This control server aggregates telemetry and issues automated commands out to the facility through a wide area network, using telephone lines, radio, or satellite. The commands eventually reach the field sites. At these sites, specific endpoint hardware like programmable logic controllers, remote terminal units, and intelligent electronic devices directly manipulate the physical valves, breakers, and motors. Whether an engineer is turning a dial or a hacker is deploying a malicious payload, the command must successfully navigate this exact pathway from the control center to the field site to affect the physical world. In July 2010, security researchers discovered Stuxnet. This diagram illustrates how the initial infection bypassed the wide area network and firewalls completely. Attackers used a physical USB drive, connecting directly to the engineering workstations. Once inside, the malware deployed a Trojan designed to target specific Siemens SCADA models running on the Master Terminal Unit. To remain hidden, Stuxnet utilized a rootkit. This cloaking software intercepted system signals, preventing the human-machine interface from displaying anomalous mechanical readings. Stuxnet then accessed the system using hard-coded passwords. It sent manipulated industrial control files directly from the MTU across the network to infect the programmable logic controllers at the endpoint. The malware uploaded stolen operating data to a remote system and waited for specific execution instructions, confirming it was a tool built for targeted physical sabotage. The weapon compromised systems across China, India, Iran, and Indonesia, and researchers believe it contributed to the failure of an Indian communications satellite. Stuxnet proved a closed network offers zero protection against a multi-stage cyber weapon designed to manipulate physical infrastructure. Deliberate attacks are only part of the threat landscape. The hardwired interdependence of SCADA systems makes them inherently fragile to systemic cascades, even without threat actors. In August 2003, a single SCADA-related software monitoring failure at an Ohio utility firm triggered a massive chain reaction. A breakdown in human communication worsened the crisis. the Ohio operators failed to notify controllers in neighboring states, blinding the rest of the grid to the incoming electrical surge. This map of the Northeast grid shows the physics of the cascade. When the initial Ohio power plant failed, electricity was automatically drawn from neighboring facilities to compensate for the loss. This automated shift had immediate kinetic consequences. The overloaded power lines heated up, sagged into inadequately trimmed trees, and shorted out, causing further line failures. The system began drawing power from surrounding states, overloading and shutting down 256 power facilities across grids in Ohio, Michigan, Ontario, and the U.S. East Coast. A single inadvertent software glitch left 55 million consumers completely without electricity. Entire metropolitan infrastructures went dark, forcing citizens to rely on literal torches to navigate the night. If a minor software malfunction can escalate into a multinational crisis, a deliberate, coordinated attack on these exact same interconnected vulnerabilities would be exponentially more devastating. SCADA systems operate invisibly behind the scenes of modern society. Basic daily activities, refueling your vehicle, browsing the internet, or preparing a meal, rely entirely on these networks functioning perfectly. They manage highly sensitive critical infrastructure, including water and wastewater treatment, like petroleum pipelines and cellular communication networks. As utility companies increasingly connect SCADA sensors to public and private networks for remote monitoring, they expose themselves to standard IT threats, like distributed denial of service attacks. This creates a critical paradox for operators. Applying standard security fixes to legacy SCADA systems can inadvertently introduce new, unforeseen vulnerabilities into the architecture. Securing the future of human infrastructure requires abandoning the illusion of security through obscurity. Cybersecurity professionals must anticipate the severe consequences of cascading dependencies, applying rigorous digital forensics equally to lines of code and the physical realities of the industrial network topology.